Reduction formulae can be really useful in integration, can save us a lot of work in integrals we could do very laboriously, and a really powerful tool. So let me show you why they're useful with an example. So here's some integrals that we can do. E to the x just different integrates to e to the x. If I wanted to do the integral of x times e to the x dx, well, that's an integral that I would do by parts, and I would say that u equals x, v dashed is e to the x, u dashed is 1, and v equals e to the x. So applying the integration by parts formula, which is here, then this integral just becomes x times e to the x minus, now I want the integral of 1 times e to the x, so that's just the integral of e to the x dx. Now, this one we can do, of course, because the integral of e to the x is just e to the x, and notice that it was also the integral that I wrote down up here, so I can just actually say that's x e to the x minus e to the x, and if we like as well, we can have our constant of integration. Okay, so next one, integral of x squared e to the x. So you can see what I'm doing here. I'm increasing the power of x each time. So this time we'll have u equals x squared v dash equals e to the x. So u dash is 2x, and v equals e to the x. So applying the integration by parts formula, that gives me x squared times e to the x minus the integral of 2x times e to the x dx. What we notice here is that this integral has essentially been reduced into one of the form above. Same here, this one got reduced into one of the form above. Here I've just got 2 times the previous integral that we had before, which was x e to the x. So this is x squared e to the x minus 2 times this whole thing here, x e to the x minus e to the x. And again, we've got this arbitrary constant outside. So noticing that this integral was one we'd already done saved us a lot of work here rather than having to do this integration by parts again. And that's really the crux of how a reduction formula works. So let's just go one more step with this. And if we apply integration by parts to the next one, then x cubed e to the x, that would be, so this time we've got u equals x cubed, again v dashed is e to the x, so u dashed is 3x squared, and v equals e to the x. So applying the integration by parts formula, we've got x cubed times e to the x minus, this time, 3 times the integral of x squared e to the x times dx. And I could work this out again now, because I can see, look, this is the integral of x squared e to the x. I've just done that before, and we know it's this whole thing. I could just replace this integral, so we can build up and up. Whereas if I'd started with this integral, of course I'd now need to integrate this by parts again and again. So this is saving us potentially lots of integration by parts. So now we've got to try and set up what I actually mean by the reduction formula. So these are all instances of the same type of integral in a way. So I might let me call this first one here I0, this second one I1, I2, and this one I3. So I'm saying these are all integrals. This is the 0th one, first one, second one, third one. And, you know, in general here, I could say, well, what would n be? Well, that would be the integral of x to the n times e to the x dx. And if we look at what we've got above here, we might take a guess and say, when I had I3, it was x cubed e to the x, I2, x squared e to the x, I1, x e to the x, I0, you could think of as x to the 0 times e to the x. So it looks like this might be x to the n times e to the x. And here I've got 3. Here I had 2 lots of the integral. Here I had 1 lot of the previous integral, and not relevant to the first one. But so we've got, I could say maybe this is minus n times the integral of one lower order. So rather than x to the n, it's x to the n minus 1 times e to the x dx. And what I've written here, integral of x to the n minus 1 e to the x, that's the previous integral here. So actually I could just write that as I n minus 1. And this thing here that I've just written out is what I'd call the reduction formula. And obviously it's not good enough for us just to spot this pattern here and to say that that's true. I need to prove that reduction formula. But the idea would be not to start by doing this necessarily, but if I could just establish this reduction formula, then I could use the reduction formula to build up the integrals as I've done. So let's try and do that, and actually we can just integrate this by parts. This is going to be a general form of what I was doing each time, so it makes sense that I'm just going to do the same thing as I did before, but in general. So I get u is x to the n, v dash is e to the x, u dash then is n x to the n minus 1, just differentiating that, and v would be e to the x. So applying the integration by parts formula, I've got u times v, which is x to the n times e to the x, which is what I want down here, minus the integral of this times this, so that's n x to the n minus 1 times e to the x dx. So we can see that this is x to the n e to the x. I could just, n is a constant, it's just a number, it's not got any x in it, so I can say x to the n minus 1 e to the x dx with the n outside here, and this is exactly what we've called in minus 1, and this is exactly what we've called in. So I do have here that in is equal to x to the n e to the x minus n times in minus 1. So I have established that this reduction formula is true in general. Perhaps a bit clearer if I get rid of all of that working there from the integration by parts. I've just got this in is equal to all of that, which is what we wanted. Now, if we've got that, then we can combine it with doing a really simple case of the integral to build up more complex ones. So, for example, usually the easiest thing to do is to do either I0 or I1. So actually I0 here is just x to the 0 times e to the x, which is just e to the x dx, and that's e to the x. Okay, plus a constant. Let's not worry about all the constants. They'll all just stay as arbitrary constants as we go through. And now once I've got that combined with this reduction formula, I can say, okay, what would I1 be? Well, it's just x to the 1 times e to the x, so that's just e to the x minus n. Sorry, it's x times e to the x here, which is x to the 1 times e to the x, minus n, which is 1, times the previous integral I0 here, which is just e to the x. That's what we found before. Similarly, if I want to do I2, I can just say it's x to the 2, just applying this formula with n equals 2, times e to the x minus 2 lots of in minus 1, the integral we got before. This is exactly the structure of what we saw when we worked out all those integrals, but now I can just keep plugging this in confidently. I3 is x cubed e to the x minus 3 times I3, and I could put all of that I2 in here, x squared e to the x minus 2 times x e to the x minus e to the x, etc. Okay. Now this is particularly good when the integral I want to look at is one that just involves a definite integral. So here, instead of just doing the indefinite integral, which still has lots of algebra in it, I replace this with a definite integral. So I've got my in is the integral between 0 and 1 of x to the n e to the x dx, and let's say I'm actually interested for some reason in the value of x to the 4 times e to the x dx between 0 and 1. So that's my target, and that is I4. Because we've established this reduction formula for this integral, which is obviously exactly the same if I put limits on it. I've just got to put my limits around the equivalent things here, and this integral have limits in it as well. I can work out I0, which is the integral between 0 and 1 of e to the x dx, which is just e to the x between 0 and 1, which is e to the 1 minus e to the 0, which is just e to the 1 then minus 1, or e minus 1. And now if I want I1, I just need to do x to the n times e to the x, i.e. x to the 1 times e to the x between 0 and 1, minus 1 times this integral I got before, e minus 1. When these things are just numbers, these numbers can simplify down. So I've now got 1 times e to the 1, which is just e minus 0, minus e minus 1. So actually for this integral, I1, I just get 1. So that's a nice result. It just says that the integral of x times e to the x between 0 and 1 is 1. And then I2 is equal to, by the reduction formula, x squared e to the x minus 2 times I1. And I1 is just 1. Sorry, this is between 0 and 1. So now I get x squared is 1 times e to the x times e to the 1, so that's just e minus 0. And then minus 2 times I1, so minus 2, so I get e minus 2. So there we go, I've got I2 is e minus 2. I3 then is x cubed times e to the x between 0 and 1 minus 3 times I2, which is x cubed times e to the x evaluated at 1, which again is just e, again minus 0, and now minus 3 times e minus 2. So I get e minus 3e plus 6, which is 6 minus 2e. And finally we get to the one that we actually wanted, I4, and I4 again is equal to x to the 4 e to the x between 0 and 1 minus 4 times I3, so that's e minus 0 again, minus 4 times 6 minus 2e, which was I3, and that's e minus 24 plus 8e, so that's 9e minus 24. So that saved us an awful lot of work there. Imagine how much algebra we would have had to do if we actually worked out the definite integral of x to the 4 e to the x and then substituted in 0 and 1 into that. This is a much quicker procedure. So reduction formulae really come into their own for these definite integrals, where the thing we're putting in here is not just an indefinite integral with algebra in it, but it's just a number essentially.